Hello everyone. Have you ever heard the famous story of Newton watching an apple fall from a tree? Whether the story is legend or fact, it inspired one of the greatest leaps in physics, the idea that the same force pulling the apple down is also keeping the moon in its orbit around Earth. Newton realized if the moon is constantly falling towards Earth but never crashes, then perhaps gravity is universal. It acts everywhere, not just on apples. Let's compare numbers. The moon revolves at a distance of about 3.84 times 10 raised to the power 8 meters. Its time period is 27.3 days. If we calculate its centripetal acceleration using the formula equals 4 pi squared are divided by t squared, we get a very tiny value compared to 9.8 meters per second squared here on Earth's surface. This showed Newton that gravity weakens with distance and perhaps it decreases as the inverse square of the distance. That idea became his universal law of gravitation. Newton's law is elegant in its simplicity. Every particle in the universe attracts every other particle. The force acts along the line joining the two masses. Its magnitude depends on two things. First, the product of the masses, m1 multiplied by m2. Second, it decreases with the square of the distance between them. Mathematically, the force is written as F equals g multiplied by m1 multiplied by m2 divided by r squared. Here g is the gravitational constant. So whether it's the pull between Earth and Sun, you and Earth, or even between two pencils lying on a table, the law applies everywhere. Of course, force is a vector. It has both magnitude and direction. If we place 2-point masses, m1 at position r1 and m2 at position r2, then the displacement vector is r2 minus r1. The gravitational force on mass 2 due to mass 1 is F12 equals minus g multiplied by m1 multiplied by m2 divided by r cubed multiplied by vector r. The minus sign tells us something crucial. The force is attractive, always pulling the masses together. And by Newton's third law, F12 equals negative F21. In other words, the pull of Earth on the moon is equal and opposite to the pull of the moon on Earth. That's why tides exist. Both bodies influence each other. What if there are many masses around? Then the total force on one body is simply the vector sum of all individual forces. This is called the principle of superposition. Each gravitational pull acts independently, unaffected by the presence of others. So if you're calculating the force on a planet from both the Sun and Jupiter, you just add the two vector forces tip to tail. This principle makes the universal law powerful. It can handle not just two-body problems, but complex systems like galaxies. Now here's a fascinating result known as the shell theorems. If you're outside a uniform spherical body, like Earth, the force of attraction is as if the entire mass were concentrated at the center. That's why we can treat Earth as a point mass when calculating satellite orbits. But if you're inside a hollow spherical shell, the net force on you is zero, all the pulls cancel. Isn't that amazing? Unlike electricity, there's no gravitational shielding, but inside a perfect shell, gravity balances out in all directions. These results greatly simplify calculations for planets and stars. Let's solve a classic problem to see the law in action. Imagine three equal masses m at the vertices of an equilateral triangle, side length 2 meters. At the centroid, we place a fourth mass of 2m. What is the net force on it? Step 1. Calculate the force from each corner. Using the formula F equals gm1m to divided by r squared, each force has the same magnitude but points in directions 30 degrees apart. Step 2. Resolve the components along the x and y axis. By symmetry, the horizontal components cancel and the vertical components add up to 0 as well. so the net force is zero. The mass at the centroid experiences no gravitational pull in any one direction. But if we change one mass, say double the mass at vertex A, symmetry breaks and a net force appears. This example shows how powerful symmetry and superposition are in gravitational problems. So let's recap. The universal law of gravitation tells us every particle attracts every other with force proportional to the product of their masses and inversely proportional to the square of their distance. The force is attractive, equal and opposite, and acts along the line joining the masses. With superposition, we can handle multiple bodies, and with the shell theorems, we simplify spherical systems. From falling apples to orbiting satellites, from tides on Earth to galaxies in space, this one law unifies them all. I hope you now see how Newton's insight transformed our view of the universe. That's all for today's session. See you in the next class with another fascinating journey into physics.